Hello and welcome to the second lab of Physics 2, Lines of Charge. In this lab we're going to be making a model that will better predict the charge of two pieces of tape that we observed in the Lab 1 experiment. So in the Lab 1 experiment we modeled the two tapes as point charges, but in this lab we're going to be instead modeling them as line charges. The line charge from the top tape, which will be composed of point charges that are evenly spread across the length of the tape, will be subject to electric forces, which are going to cancel out with the force of gravity that's working against this top tape to equal zero net force, which is what will be necessary for it to float. In this lab, we're going to be using the same equations here that we used in Lab 1 in order to calculate the electric field and the electric force on a point charge. And we're also going to be using this approximation of an electric field from a line charge, where we break the line charge up into n pieces delta Q, where each charge is equal to the total charge divided by n. Here are the measurements from our experiment. They're the same measurements that we had in Lab 1. For our computer model, we're going to treat the upper tape as a system and the lower tape as the surroundings, and we're going to break up the total charge on each tape across n pieces of the tape, evenly spread out from one another. We're going to treat these pieces as point charges and use iteration to calculate the total interaction of each charge on the top tape with all the charges on the bottom tape. And we're going to visualize the electric field at the location of each charge on the top tape, as well as the total electric force on the top tape, that sum of forces as a result of the electric field and the force of gravity on the top tape. And we're going to balance these forces with gravity, the total electric force with gravity to equal zero. So we're going to use a guess and check strategy for Q until the net force equals zero. So here we have our glow script model. We start with our constants. Then we have our function for calculating the electric field, which we brought from Lab 0. We have our function for calculating the line charge, given a starting position, axis, mass, charge, etc. The important parts here is calculating the magnitude of each point charge, where we divide the total charge by n being the number of pieces that we break our tape into, and of course doing the same for the mass. We have our top and bottom tapes here with our position vectors, mass, n equals 20. Down here we calculate our total electric field by summing all of the electric forces from the bottom tape point charges on each individual point charge on the top piece of tape, and we sum those together to get this total electric field. And then we visualize the total electric force and the total force of gravity by drawing arrows. So when we run it, we see that we chose a correct value for the total Q, as our magnitude for the electric force and gravitational force are about equal. Now we ask the question, what if we modeled each of our tapes as a single point charge like in the previous lab? This right here is the value that we got from our previous lab, and this is the one we got from this lab, modeling the charge as a line charge. Now we ask, why do these estimates differ? What is more likely to be closer to the real value, and why? Well, the reason that the line charge is greater than the point charge is because there are components, as you can see, when we add up all of these electric fields, they're pointing in the positive or negative x direction. These components are going to cancel out with one another, and so you're not getting just one vector pointing in the negative y direction, which would be more efficient, and thus you wouldn't need as great of a force. And so because there are x components to the electric fields and these cancel out, you're going to require a larger force to cancel out with gravity. So in conclusion, we're starting to be able to model the total charge of a three-dimensional object more accurately than we would if we were just to approximate it as a point charge. And we discovered that by breaking up a complex object into simple components that we know how to work with easily, we are able to make a fairly accurate approximation of the charge for that object.